we go. All right, so I think it's all good because you can see the volume, or the signal bar, jumping a little bit. All right. So I wrote a new piece. It's called address versus integer. If you scroll down a little bit, it's the last item, address versus integer. So what I'll do is not really just reading the content here, because reading to me is really boring. So I would much rather be doing experiments. Okay, so I would actually show you, a program, and as we write and try to compile the program, I'll use GDB to illustrate the concepts. Yes?
Before we do that, we explain how we convert bit numbers into hexadecimal.
Oh, right. Okay, so binary numbers to hexadecimal. Let's do that first. That one, you can do it with a table. Okay, a table lookup is basically what you need in order to convert from base 2 to base 16 and back. It is a lot easier compared to base 10 to base 2, because base 10 to base 2 requires a lot of division, or at least comparison. But this one is really easy. Okay, so let me start with a new spreadsheet. And in the new spreadsheet here, the first thing I do is I will write down the binary numbers. We only need to write down 16 binary numbers, because what is 16 is a power of 2, but what is the power? Is 2 to the power of 4. Okay, very good. So that means that the quantity that I can represent using 4 bits is the same thing that I can represent using one base 16 digit. Is that making any sense? So in one system, I have 1, 2, 4, 8, $16 bills. In the other system, I have $1 bills, $16 bills, $256 bills, and so on. Okay, because if you look at the number base, like the currency, that's basically what we have. So in one system, if we use binary, which means 1, 2, 4, 6, 1, 2, 4, 8, 16, and so on, we will need 4 different bills to add up to 15. Okay, because it's 1 plus 2 plus 4 plus 8. Okay, that adds up to 15. But if you use base 16, you have $1 bills, and then you have $16 bills, and so on. So with a 16, with base 16, you just need 15 $1 bills to make up the quantity of 15. You don't need to move on to the next denomination, which is 16. Is that making any sense? Sort of? Maybe?
I was good up until that.
Sorry?
I was good up until that.
Okay. Okay, so think about well, let's do this with numbers first, and then we'll talk about the other one. So this is just binary numbers. The next one is, what is the next value in binary? 1. Okay, what is the next one? 1, 0. Because if you add 1 to 1, we normally get 2 in base 10, but in base 2, you have a carry, because you can only represent up to 1 per digit. Okay, and the next one is going to be what?
1.
Yep, and the next one?
0,
1, 0, 0, because if you end up with 2 carries before you can settle down. Okay, and this one is going to be 0, 1, 1, 1, and then we have 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. Yep, go ahead.
Oh no, I'm just stretching.
Oh, okay, gotcha. All right, so are there any questions about this particular sequence of binary numbers? Basically, they represent from 0 up to 15 in base 10. So in the next column, which is column B, I'm going to just write down these values in regular base 10 representation. So we have 0, 1, 2, 3, all the way up to 15. But before we go any further, let's just pick one number and see whether it makes sense or not. Let's just pick this number here. 1011 in binary. What is the quantity it is representing? We have 1, 1, we have 1, 2, we do not have any 4s, and then we have 1, 8. So it's 8 plus 2 plus 1, which is 11. And that's exactly what we have here, which is 11. Is that okay? How to read a binary number? Okay, so the next thing we'll do is to write down the digits in base 16. So column C is going to be base 16. Base 16 can borrow everything from base 10 all the way up to 9, okay? Because we do have 9 digits in base 10. But we don't have a single digit to represent 10 in base 10, because that's the whole idea. When you get to 9, you have to have a carry, and then you roll back to 0 for the least significant digit. So what we do here is we borrow from the alphabet. Then we say this is A, and this is B, C, D, E, and F. And this doesn't look good because the numbers are all flushed to the right-hand side, and then all the letters are flushed to the left-hand side. So that makes it a little bit better. Not a whole lot, but just a little bit. So are there any questions about these 3 columns at this point? This is what I meant by column lookup, a table lookup, because every time you're presented with a hexadecimal digit, which is one of the things in column C, you just have to look up column A for the equivalent binary representation. And it works really well because there's no need to do any division. And the reason why there's no division involved is because these 2 tables match up exactly. Because the next one, if you want to work out the next one here, the next one here is going to be what? 1, 0, 0, 0, 0 in base 2. But in base 16, you are running out of digits as well. So it has to be a 1, 0 in base 16. So when you have to use more digits, they both have to use more digits at the same time. And that's why they line up so well, because every 4 binary digits is 1 hexadecimal digit. And that's why we can use a table lookup method to do the base conversion. It does not involve multiplication, does not involve division at all. It's just really quick and easy. Yep.
Okay. On the test, is anything like this going to come up where we're going to need the table, or are we just going to have to?
You can, well, the next exam is going to be open book, open notes as well. So I would,
So just put it in the table?
yeah, just put it in a table and bring it along, just in case.
Okay.
Because this sort of thing is really useful if you're getting into computer science. It's going to be really useful anyway. So and it's really just a table lookup too. So you just put this table into your cheat sheet and you're done.
Okay.
Yep.
So why does it go in the binary representation? We're only going up to 15 for each representation, 16 hexadecimal. There's misunderstanding there.
You talking about row 17? This one here?
No, I guess because why is each? Because if hexadecimal is base 16, why
Right.
does it translate to each individual digit is a up to 15 count in binary? Or am I? Oh wait.
Well, let's think about an example. Go ahead.
I was going to say, just for a visual representation, could you write 33 in base 16 to show us what that would look like?
32 as a base 10 number.
33 as base 16.
So 3 as base 16.
Yes.
Okay, so 3 as base 16, the way that we do it is like this. And I can use a editor to do this part here. So if you want to do 3 in hexadecimal, right? Okay, so the way we represent this is base 16 instead of base 10 is the 0x prefix. When you see the 0x prefix, it means the following number is expressed in base 16 and no longer in base 10. Okay, so that's the first convention. The next thing we do is we look at each digit, starting with the least significant digit, and say, okay, this is 3, but what does it look like as a binary number? It is 0, 0, 1, 1. The leading zeros are important in this case. So every time you map a hexadecimal digit into binary, you have to use exactly 4 binary digits. 4 binary digits, you cannot forget the leading zeros. Okay? So then we look at the second least significant digit, which is also another 3, and that will be the more significant part of this, which is also 0, 0, 1, 1 in this case. So the binary representation of hexadecimal 33 is 0, 0, 1, 1, 0, 0, 1, 1. Is that okay?
Correct.
So you would just write that down, you wouldn't carry the 0x with it or anything?
You mean on the binary side? You mean on this side here, the right hand side,
Yeah.
like this? Yeah, the binary number, there's no way to actually represent numbers in binary in C or C++. They do not have it doesn't recognize binary numbers. So this is only useful for our purposes, of discussion, but you cannot really write binary numbers when you're dealing with C and C++.
Alright, and on the left side, the base 16 form, that's just correct form of
Yes.
0x33?
Yep. If you write down 0x33, it means this particular bit pattern, which is 00110011.
So if I wanted to write like 256 in base 16, I just do 0x256?
Okay, are you talking about 256 as a value in base 10 expressed in hexadecimal, or
Yes.
256 as
Base
a
10 in
hexadecimal?
hexadecimal.
Okay, so if you're trying to express that particular value, 256 is actually 100 as a hexadecimal number. The reason why it's 100 is because we have 0 ones, we have 0 16s, but we have 1 256. Because when you move from one digit to the next, it is representing the quantity of 16 times the base of the previous one.
Okay, and since there can be like multiple, trying to think where to put this, that you could have 11 ones, that's where the letters come in?
You can have
So if
11
you had,
ones.
it's 256 plus 11.
Well, let's try
267.
31 as a value.
Okay.
Okay, let's try 31 as a value. So when I say 31, it is explicitly a base 10 number, because otherwise I would have said 31 in whatever base. Okay, so when I say 31, it is actually the 31 the quantity. So when you look at 31 as a base 10 number, and you say, okay, can I identify any components that is a power of 16? Okay, where do we start? Well, 256 is a power of 16, right? It's 16 to the power of 2, right? Do we have any 256 in 31?
No.
No, so we can forget about it. What about the next one down?
We have 116.
We have 116, very good. So then you say we have 116, and after we take care of the 16, what is the quantity left?
15.
15, so we have 15 times 1, right?
Yeah.
So the next thing you do is to look at the 16 not just as 16, but look at it as 16 to the power of 1. And then you look at the 1 not only as 1, but look at it as 16 to the power of 0. Because that explains why we have this one here. Because the next step is to convert this actually into hexadecimal representation. So we have a 1 here, but since we do not have a single digit in base 10 to represent a quantity of 15, we have to borrow from the alphabet. Do you guys remember which digit is actually still on the screen? Which letter is representing 15?
F.
Yep, that's it. So 1F as a hexadecimal number is representing 31 in decimal. Now since we have the lookup table, we also know that 1F in hexadecimal is 00011111 as a binary number. Yep, go ahead.
So for the hexadecimal 33, why isn't it shown? Okay, never mind. I get it.
Okay, so the next question is, I think some people may have this question, is, why do we need to understand hexadecimal numbers, base 16 numbers? If I'm not going to be a programmer, if I'm not going to be a low-level type of programmer, why is it important? Yep, go ahead.
For hexadecimal color coding, if you want to do like
HTML. Yep, for HTML color coding. And for those of you who kind of mess around with networking a little bit, you might find yourself learning binary numbers and hexadecimal numbers, because if I try to look at a particular network card, okay, and this is a good one right here, right there. Okay, so this particular number is called the MAC address of a network card. Okay, it uniquely identifies a particular interface, a network interface, on a segment, on a network segment. Okay, what does it look like to you?
Looks like a bunch of letters and numbers.
We have certain letters and mostly digits. Okay, but when you look at the letters, is there a particular range?
Looks like you can only do like.
Well, for this particular one, it only goes up to D, right? But it does not exceed F. There are no G's or beyond, right? And that's because why? Why do you think it is represented as 6 hexadecimal numbers, and each one only has 2 digits. Now, one hexadecimal digit is representing 4 bits, right? So 2 hexadecimal digits will be representing how many bits? No. 8 bits, okay? And 8 bit is also known as a very basic unit of measuring. It's a byte, exactly. So so a MAC address is actually made out of 6 bytes in this case. So looking at this, I can see exactly the bit pattern for this particular MAC address. It's 1000 for the 8, 1100 for the C, 1101 for the D, 1100 for the C again, 1101 for the D, 0100 for the 4, 0010 for the 2, and so on. Okay, I know for the rest of it it's going to be boring, but you guys know the general idea. But why do I want to express stuff in binary?
I have no idea.
So a computer can understand it?
Because that's exactly how it is represented in a computer. Okay, everything in a computer, like this type of computer, or most computer, including your cell phones, they're all zeros and ones. Okay, everything boils down to zeros and ones eventually. So that's why we want to be able to represent zeros and ones fairly easily. The other one would be these two. Okay. Okay, well, we'll take a look at this one first. Okay, this is INET6, which is basically IPv6. This is the IP address in IPv6 or Internet Protocol version 6. It's a whole bunch of numbers, right? But these are all hexadecimal numbers. In other words, someone can look at this number and identify a unique computer on the internet. That's basically what it is. It's a phone number applicable to the internet. Now, when you look at the other number, it doesn't look like it's not a hexadecimal number. This is actually all in decimal. But when you look at each segment, it can only go up to 255. In other words, 84 is going to use up 1 byte, 100 or 100 is going to use up 1 byte, 196 is going to use up 1 byte, 165 will use up another byte. In IPv4 or the version 4 of Internet Protocol, each address on the internet is represented by exactly 32 bits or 4 bytes. But in IPv6, it is represented by how many? It's a lot more. So we have 1, 2, 3, so 2 times 5 is 10 bytes. Yep, so we can address a lot more devices on the internet using IPv6. All right. Bob, do you want to do the evaluation first or not? Okay, carry on. Okay. All right. So I just want to illustrate, why it is important to understand, base 2 numbers, because we are used to base 10 for only one reason. We got 10 fingers. Okay. And if you ask me as a computer science person, that's a hindrance. Okay. I would much rather we either have 8 fingers on each hand, or 4, or 2, or just 1. Okay. Having 10 fingers is really not a good way to do things from many perspectives. But we are so used to base 10, sometimes it's hard for us to get back to base 2, which is a lot easier for a lot of different things. All right, so is that particular question answered? Base 16 and stuff like that? All right, okay. So with that question answered, we are going back to this slide here because I want to continue to talk about what is an address and what is an integer. Okay. Well, there is difference. Well, okay, let me just kind of read my own question here because it is significant. If an address is really just a bit pattern like an integer, then how is it different? How is an address different from an integer? So the next paragraph is asking a little bit more because I explained it's a tricky question to answer. From the perspective of the processor at the lowest level, there really is no difference between an integer versus an address. A 32-bit bit pattern is a 32-bit bit pattern. I know it sounds kind of Buddhist or Taoist, but that's basically what it is. Okay, 32 binary digits is just 32 binary digits. How you use it determines what it is. Okay. So what makes the difference is how the 32-bit number or bit pattern is going to be used. And that's why we learn about types. Do you still remember what a type is? Even though up to this point we have only been using integer types, but what exactly is a type? What is the purpose of a type in a programming language?
An abstraction for programming use.
Well, but what does it do? What does it actually do when you're dealing with a program with types? Go ahead.
It specifies the type of data that can be stored in the variable.
Okay. Well, it actually specifies what you can do with a particular value. Okay, if you have integers, you can do a lot of things. You can compare, you can divide, you can subtract, you can multiply, you can take the remainder out of a division, right? If it's an address, what else can you do with it? Well, you can follow an address, right? If it's an address, you can follow the address and go to the location of that particular address. So what I have here, I'm skipping a few things and skipping down here. So we'll first consider this particular snippet of code. Everybody understands what this one is, right? Okay, the first line is declaring x is an integer variable, not initialized. And then the second line is saying, okay, let's store a value of 20 into x, and that's the end of it. Okay, are there any questions about these two lines of code? Okay, no questions? We all kind of know what this is, right? So what we're going to do next is to introduce the concept of an address. So what I'm doing here with the second line is a little bit tricky, okay? The right-hand side is still 20, which is just a quantity of 20, but the left-hand side is now something else, okay? What is this part here? What is int star doing within this code? How do we call this? It's a typecast operator, okay? In other words, we are telling the compiler and say, forget about what you knew about x, okay? I'm telling you, treat x as if it is it's a pointer to an integer or an address of an integer. This is where the syntax of C gets a little bit confusing because you have to read it backwards. Because this asterisk means it is an address of what? It's an address of an integer. So you kind of have to read it backwards. But together, int star, together with parentheses around it, you have to have a parentheses around this one. It means we are casting. We are telling the compiler and say, what you knew about x is not right anymore. For this particular case, treat x as an address to an integer. Okay? But the compiler will complain about this one. If you try to write a program like this, write a line of code like this, the compiler will complain because there's a problem. What exactly is 20? What is the type of 20 as a constant? It's an integer. Very good. And again, what is this side? What is the left-hand side after the typecast? Is not an integer anymore. It becomes an address of an integer. Okay? An address of an integer is not an integer. And as a result, the two types of the assignment operator do not match, and the compiler will complain and say, hey, the type does not match, you cannot do this. Okay. If that is the case, maybe we can fix the problem by casting the right-hand side as well. Yep, go ahead.
Okay, I forget what it was called when you reading materials, but so I know that when you have a variable listed up, it has a right-hand return value automatically. Is the case that's happening when you use a typecast that it's just a mismatch, or is it just it doesn't have a right-hand side value automatically associated?
You mean for this one?
Yes.
For this one, I'm trying to fix the compile time error.
I mean, just in the first case, sorry. We have the typecast just in the left end.
Oh, you mean this one?
Yes.
Yeah, this is just to illustrate, when you will get a compile time error.
Oh, no, I just mean like technical level is the reason it would cause compile error because a typecast no longer has an implicit left-hand side value to return, or is it because it's just?
It's simply because the types of the two sides do not match anymore.
Okay.
Yeah, because on one side you have an integer, on the other side you have an address of an integer, and those two types do not match. An integer must match an integer. An address of an integer must match an address of an integer. So in this case, I fixed the program by introducing another typecast operator on the right-hand side. So this will compile, okay, but it's not a very good idea. It's not a good idea because I am basically telling the compiler and say, oh, 20 is no longer an integer. Treat 20 as an address of an integer. Now, when 20 becomes an address of an integer, it implies, hey, you can go to that location, okay? You can go to the location corresponding to 20 and retrieve something from that location or store something into that location. But as it turns out, that location is inaccessible by your process, by your program. Okay? So this is not a good idea. The program will compile, it will run just fine. However, it's not a good idea to typecast 20 into an address because it is not a valid address to begin with. Is that okay so far? Okay. So now we move on to another one, which is this one here. This one will not have a compile time error, but it will give you a runtime error, which is even worse. Compile time errors by comparison are easy to deal with because the compiler can check it and it won't let you continue unless you fix all the compile time errors. But this is not going to generate a compile time error, it will generate a runtime error. So let me explain what this one is going to do. The right hand side is easy. The right hand side is just 20 as an integer. The left hand side, you have to read it backwards again. We start off with x, okay? And then I say, oh, but wait, don't treat x as an integer, which is its actual type. Treat x as an address of an integer. In other words, I am treating the value of x as an address of an integer. With the highlighted portion here, that's what it's saying. Is that okay so far? Okay, so the value of x, whatever is stored in x, is now treated as an address of an integer. Well, but we already saw that this will generate a compile time error, so we have to do something about it. This asterisk here is called a unary operator because it only needs a value on one side. It is called a dereference operator. Now the dereference operator is going to reverse the address of operator that we talked about last time. What it's going to do is to say, give me an address, I will go to that location. Okay, I'm going to follow an address, get to the location, and if this is on the left hand side, I will store something at that location. If this is on the right hand side, I will retrieve the content at that location. Is that okay so far? Okay, so let me just kind of repeat the entire thing. Here's x, which is just an integer. This time, with this part, I am typecasting and say, treat the value of x as an address of an integer. But because it's an address of an integer, I can now follow the address and get to that location. That's the asterisk here. So I'm going to use the value of x as an address, go to that location, and then we store 20 as a value into that location. Which location are we talking about? Sorry? But whose address? I am using the value of x as an address, and I will try to store 20 into that location. But which location am I talking about? What is the value of x to begin with? It's uninitialized. I have never put any specific value into x. So that means x itself is uninitialized, which also means the address of an integer, because of the typecast, is also unknown. I have no idea which location we are talking about. But I'm going to blindly follow that address and say, I'm going to store 20 into that location. So out of a 4 gigabyte memory space, because of the 32-bit thing, we have access to maybe 5 megabytes or so. What are the chances that this will end up as an actual location that you have access to? Pretty low, okay? So that's why, when you write a program like this, it will crash because it will try to store 20 to a location that is not specified, that is uninitialized. Yep.
How is it uninitialized when it says x equals 20?
But that's not what it's saying. It is saying use the value of x as an address, follow that address, and store 20 to that location. That's what it's saying. But x is uninitialized, which means the address that you're going to follow is also unspecified. You're trying to specify, Okay, this is nothing. This is basically somebody has a piece of paper that has gibberish on it. Okay, that's how variables start to exist. Is it has gibberish. Okay, so somebody gives you a piece of paper that is just completely gibberish. Okay, I pull a piece of paper out of the recycle bin. Okay, and I give it to you and say, whatever is on this piece of paper, treat it as an address and go to that location. And here's a package to deliver to that location. See ya. That exactly. Well, you probably will end up somewhere in the ocean, okay? Because if it's a GPS location, it's uninitialized. I just give you two random numbers. You have to use one as the latitude, use the other one as the longitude, and that's where you have to deliver the package. Is that okay?
Just so I understand the function though. So what happened is, when you typecast it as location of an int for x, it's literally just saying whatever number is in x, I will interpret as an address location.
Exactly. You are telling the compiler, I know what I'm doing. Just do it as I say. Which is, and that applies to all typecasting in C and C++. So you have to be very careful when you typecast something in C and C++ because that's basically the compiler releasing its liability and say, okay, if you say so, I'll do it.
Okay. And then follow up, I guess, for the dereference operator.
Yep.
Does it implicitly cast anything fed into it as an address, or is it going to?
It is implicitly, it basically takes the address of whatever. Now, because this part says it's an address of an integer, and you're following the address, so it becomes an integer. So it is pretending that that location is supposed to store an integer. Okay? All right. Well, let's go to this one here. Okay, this one is kind of.
Before you proceed with that one, so what's the main difference between the first one?
The first one?
When you typecast to the right.
You mean this one?
No, yeah.
You mean this one?
The second one. The third one?
This one?
Third one.
Third one.
Yeah.
This one?
Yeah, and then.
Okay, so let me highlight those two. So you're talking about this one
Yeah.
versus this one.
Yeah.
Okay. Well, okay, the biggest difference is the dereference operation. Is there any dereferencing being done here?
No.
No. So that means I am treating x still as a variable on its own, except the type of the variable is no longer an integer, it is now an address of an integer.
And then the other one, yeah, referencing back to.
The other one, this part is the same. You can see this part is exactly the same, right? But then this one also has a dereference. Okay, now that means I am going to use the address specified by this part and use that to go to a particular location in order to store the 20. So that's why it's really fundamentally different. This one is still using the piece of paper that I gave you from the recycle bin and say, okay, this piece of paper, even though it says it's supposed to store an integer, go ahead and store an address in it. Okay. The other one is saying, okay, here's a piece of paper. Whatever is on it, treat it as an address. Go to that location and then store the value. Okay. There's a last one too. Okay. This actually. Okay. So obviously at this point, this is bad news. Okay. This program will crash. Okay. It will crash, and it will give you a segmentation fault. Okay. There are very few cases where this is not going to crash because X may just accidentally correspond to a memory location that you do have access to. But what is it? I don't know. It can be anywhere in memory that you have access to. That makes it even worse. Crashing is good because it stops right away. If it doesn't crash, it will overwrite some location and not to give you any symptom. It will just continue to move on until such time you actually have to use the corrupted piece of memory. Then your program will crash. But when it does crash, it is so far out beyond the actual cause of the problem, you would not know why the program crashed. Okay? Now this, by the way, will not happen in most other programming languages. In Visual Basic, this cannot be done. You cannot do this type of harm to your own program. There's no typecasting that can turn an integer into a pointer in Visual Basic. Is that right, Bob?
Correct.
Yep. And that helps to protect your program, because you cannot just tell your Visual Basic program and say, I know what I'm doing. This is not an integer. This is an address. Treat it as such. I want you to follow this address, go to that location, do something. You cannot do that. You cannot convince Visual Basic or Java to do this. Only C and C++ gives you this flexibility on one hand, but it's also a curse on the other hand. Okay? Now we move on. There's a happy ending to this whole thing. Okay? This is the happy ending. And when you look at the happy ending versus the one that crashes, there's not really a whole lot of difference, right? Okay, just look at this line of code here and compare that to this line of code. What is the difference?
Store by reference?
No, it's not stored by reference. There's an ampersand, right? Okay, so let's go ahead and read this code here, the highlighted portion. And well, it's all explained here as well. Okay, so if you want to read it on your own, that's fine too. But let's go ahead and read this part, only the left-hand side, and let's see what it's saying. This is x, which is an integer. And from the previous class, we know what the ampersand is. As a unary operator, what is ampersand doing? It's in the text.
It returns the address of.
It is the address of. Okay, so together, ampersand x is the address of the variable x. Okay, first question: is the address of variable x some place that your program has access to?
Yes.
Yeah, because it is a variable. Okay, by this time the variable does exist. So the address of x is a good place, okay, to store something or to retrieve something. Is that okay? And what am I telling the compiler to do? Well, I'm telling the compiler to do something that is completely redundant. X is an integer, so the address of x is an address of an integer. Very good. And I'm casting it into an address of an integer. I'm telling the compiler, hey, I'm giving you an address of an integer here, and treat it as an address of an integer. Do you detect the redundancy of that sentence?
The other side.
Yeah, it doesn't need to be there, okay? But being there doesn't do any hurt either. It's just like, okay, it's not really needed. All right, so the highlighted portion here is basically saying, I explained it down here as well. Okay. Well, if you read this part, you will know, I explained that in English as well. So at this point, we have, the address of an integer being treated as an address of an integer. One thing you can do with an address that you cannot do with an integer is to follow the address, okay, which is the asterisk symbol right here. This is the dereferencing. So I'm going to follow an address of an integer that is treated as an address of an integer. Is that okay? I'll say that sentence again. Okay, I am. Okay, let me highlight the operator as I say it. I am following an address of an integer that is treated as an address of an integer. That's okay, right? And I'm saying I want to store the value of 20 at that location. What does it actually do?
Stores 20 in x.
It stores 20 into x, okay? So when you read this part here, then you will actually get a sense of, hey, this operator, okay, following the address of or dereference, is canceling out the effect of the address of. Because one is extracting the address of something that can be stored that has a memory location corresponding to it, and then the other one is saying, oh, let's follow that address. So one refers to the address, this will get the address, this will get to the content, but if you use another ampersand, it will get to the address again. So that means, okay, let me just skip to the part here. In other words, these two expressions are really exactly the same. This expression here, and you can definitely tell that this can extend indefinitely long, meaning you can have more asterisk and ampersand pairs. It's really the same thing as saying x. Because ampersand and dereference, or ampersand and asterisk, they cancel out each other. Is that okay? Okay. So if that is okay, we are going to use GDB and play with this a little bit. Okay, so we'll go to the temp folder And let's test a particular program. We'll use exactly the same kind of code here. Most people say C++ is not interactive. Well, that's before they get to know GDB, because GDB makes C++ interactive. Okay, so we'll go ahead and just say x equals to 20, and then we'll have the other lines of code. This one will not compile, and then we have this one here that will compile, but it's not a good idea. And then we have this one here that will compile, but it won't run. It will crash the program. And then we have the last one, which doesn't really do anything that is new, because it just does the same thing as the first line of program. So these are the 5 variations that we have talked about. Okay. The first thing we'll do is we'll just go ahead and compile the program and confirm that one of these will have a problem. The compiler is not going to like it. Okay. All right, so save the program and then say g++-c-g, which is not really needed because it's not going to compile. And sure enough, it actually gave us 2 errors. Okay, so the first one is on line 6. That one we know because 20 is an integer, and once you cast x into an address of an integer, it is no longer an integer, so it complains about it. And then on line 7, it complains about that one too. It complains about L value required as left operand of assignment. So casting x into an address of an integer does not, it wouldn't let me do it. It's basically saying it's an address. We cannot store something into an address. We have to store something into a variable, a place. Okay. Are there any questions about these 2 lines of code? I did not really expect line 7 to have a problem, but it does. Any questions about this part? Okay, so what we'll do is now we change the program, get rid of those 2 lines, okay, because this one / is the symbol to get rid of a particular line. Yep. You want to do it now? Yeah. 5 minutes. Okay, gotcha. All right. So what we'll do now is to actually compile the program and run it. Okay. So g++-c-g test.cpp, g++-o test.cpp, and just run it. Segmentation fault. Okay, the program is crashing. When you deal with pointers, you can expect your program to crash like this, okay? Which means running your program out of GDB is not going to be very helpful. Yeah, go ahead.
Wouldn't that be because you linked it wrong? You did test.cpp instead of test.o?
Oh, actually, well, I made that mistake, but it's actually going to do the same thing too. Yep. All right, so let's go ahead and debug the test program, and I'll run it at full speed. Now, this is useful. The program still crashed because it says your program received signal segmentation fault, but there's one thing that really is helpful here. What is it saying? It's telling me which line is a problem. Okay, it's telling me that the problem happened when line 8, when I tried to do line 8, when the program tried to execute line 8, that's when the problem happens. Okay, so at this point, what we'll do, okay, we got 5 minutes, or we got 5 minutes. It's not 5 anymore. Okay, so x has a value of 20 at this point because of an early assignment, and we are basically saying, oh, okay, can we do something like this? Can you treat x as an address? Sure, not a problem. Okay, that by itself is not a problem. But what are we doing here? We are actually looking at the value of x, which is 20, and treat that value as an address. Oh, but why is it printing 1,4? That goes back to something that we talked about really early today. What was it? It's a hexadecimal number, 0x14. Now, knowing it's a hexadecimal number, we know the 4 is representing the number of ones. We know this 1 is representing the quantity of 16s. And that adds up to be 20. Okay? But it's basically using 20 as a location. Can we go to that location? Okay, so we say, let's dereference it. Okay, so we'll dereference everything like this, except this time I'm not going to use x here. I'm just saying, okay, because x has a value of 20, this should do exactly the same thing. Press the enter key and it says cannot access memory because location 20 is not accessible to your process. Are we good, Bob? Do you want to do it now? All right. So let's go ahead and do the evaluation. I'm going to turn off the mic, stop the recorder, and step back in when it is done.